Over the western Indian Ocean, highly active weather systems are gathering, setting the stage for extreme meteorological volatility across East Africa. The World Meteorological Organization has issued high-confidence warnings, pointing toward a prolonged period of climate instability for the region. The primary driver of this volatility is the emergence of El Niño conditions. Forecasters note that the climate models have successfully overcome the historical spring predictability barrier, aligning to confirm a highly active event. This visualization maps ocean surface temperatures. That massive red anomaly across the central and eastern Pacific is El Niño. This warming alters the Walker circulation, disrupting normal global rainfall patterns. For Kenya, this ENSO shift acts as an atmospheric engine, driving active weather systems and enhanced moisture directly into the landmass. This specific hemispheric convergence guarantees a highly volatile, highly destructive meteorological environment for the May 2026 season. The Kenya Meteorological Department has translated these macro patterns into localized forecasts. Daily rainfall will exceed 20 millimeters, with cumulative totals projected to surpass 100 millimeters in early May. In the discipline of hydrology, precipitation exceeding 50 millimeters within a 24-hour period is the recognized mathematical baseline for generating a flash flood. With cumulative projections hitting double that baseline, severe hydrological overflow and rapid onset inundation are mathematical certainties. Modern climate variables compound this threat. Climatologists calculate that climate change makes these specific extreme urban rainfall events approximately 40% more intense than historical averages. Crossing this mathematical threshold transforms rainfall into a massive, high-velocity kinetic threat, instantly rendering legacy urban infrastructure obsolete. Nairobi's exponential, uncontrolled urban sprawl has pushed thousands of informal settlements directly onto natural riverbanks and floodplains. By systematically paving and building over these designated riparian zones, the city has stripped the environment of its vital absorptive vegetation. Look at how 100 millimeters of rain interacts with the ground. Root-filled soil absorbs water deeply, but on impermeable concrete, water has nowhere to go, rapidly pooling. This massive runoff accelerates into aging, blocked artificial drainage systems, which fail almost instantly. The water inevitably seeks the path of least resistance, channeling its massive kinetic energy directly into arterial roads and underpasses. This infrastructural collapse carries a heavy economic toll. In recent events, repairing damaged road networks alone required an estimated $300 million. Urban flash flooding is a failure of design and volume management, manufactured by the physical composition of the city itself. Pedestrians face a dangerous psychological bias during these events. Murky, silt-filled floodwater completely obscures the topography beneath it, tricking the brain into perceiving a static puddle instead of a dynamic physical force. Moving water's lethality is dictated by fluid drag, increasing exponentially with velocity squared. For pedestrians, the critical threshold is just 6 inches. Water at this depth possesses enough kinetic energy to break friction, violently sweeping a person off their feet. Hidden within that moving water are severe biohazards. Overwhelmed municipal systems back up under hydrostatic pressure, discharging massive quantities of raw, untreated sewage directly into pedestrian walkways. Direct dermal exposure to this effluent drives secondary disasters, most notably the lethal cholera outbreaks that routinely follow heavy rains. There is also a silent electrical threat. Submerged junction boxes and collapsed power lines charge pools of standing water with lethal voltage. Navigating flooded urban streets on foot means voluntarily walking into a high-velocity biochemical and electrical hazard zone. The vehicular mortality rate during heavy rains is driven by an illusion of traction. Drivers consistently miscalculate the severe risk of driving through flooded roadways. Modern automobiles are engineered with exceptionally tight door seals and heavy weather stripping. In a flood scenario, these features turn the vehicle cabin into a highly sealed, buoyant air pocket. This follows Archimedes' principle. The displaced water generates an upward buoyant force equal to the weight of the displaced fluid. Once the water depth reaches the vehicle's undercarriage, frequently around 12 inches, this upward buoyant force begins to aggressively counteract the vehicle's downward mass. This reduction in downward pressure eliminates the critical tire-to-road friction required for steering and braking. If caught in rising water, the emergency egress protocol requires unbuckling and rolling down windows immediately. Once water rises past the mid-door level, inward hydrostatic pressure makes it physically impossible to push the doors open from the inside. At a depth of just 1 foot of water, buoyancy overcomes friction, turning the vehicle into an unsteerable, drifting raft. Despite the doctrine to turn around, drivers frequently attempt to push through moving water, ignoring the strict mechanical limits of their engines. An internal combustion engine operates on a precise thermodynamic cycle, drawing in a combustible mixture of air and fuel, highly compressing it within the cylinders. In terms of physics, air is a highly compressible gas. Liquid water is completely incompressible. When forced into deep water, the air intake vacuums floodwater into the combustion chamber, triggering hydrolock. The crankshaft's inertia forces the piston upward against unyielding water. Because liquid won't compress, heavy steel connecting rods snap instantly under the immense pressure. A hydrolocked engine cannot be salvaged. It requires total replacement. Simultaneously, dirty floodwater shorts out submerged electronic control units, completely disabling the vehicle's electrical systems. Entering deep floodwater results in total mechanical destruction of the engine and electrical systems. Understanding the physics of infrastructure failure proves that reactive, post-disaster management protocols are inadequate. A flaw exists in current early warning systems. Broadcasting meteorological supercomputer forecasts through traditional media frequently fails to trigger timely evacuations at the grassroots level. During previous El Niño events in the Isiolo region, communities successfully deployed a different approach: decentralized, community-managed telemetric networks. The mechanics are straightforward: placing simple ring and river gauges in local schools, upstream, which are monitored by trained focal points who can instantly signal communities downstream. This hyper-local data provides the vital hours needed to move vulnerable households and valuable livestock to higher ground before the water physically arrives. A national meteorological warning is useless unless successfully translated into an immediate, localized telemetric alert. Municipal planners must apply this preemptive strategy by aggressively deploying heavy machinery to clear urban drainage choke points well before the heaviest rains begin. Authorities must also pre-position heavy physical barricades and law enforcement at notorious low water crossings to actively remove the element of fatal human misjudgment. The geographic and human stakes are massive, spanning from the coast to the sprawling floodplains of the Lake Victoria Basin. Citizens bear a personal responsibility to respect the physical reality of fluid drag and vehicle buoyancy by unconditionally refusing to cross moving water. By abandoning a posture of reactive panic and acknowledging the strict, unforgiving physics of hydrodynamic failure, Kenya can deploy the precise scientific mitigation required to preserve human life and critical infrastructure.